turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
questions,
Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to the Naked Scientists podcast. This is a show that brings you the biggest breakthroughs and talks to the major movers and shakers in the worlds of science, technology and medicine. I'm Chris Smith, and this week, with prices at the pumps rocketing and some countries even closing their forecourts as their tanks run dry, we're taking a look at the geology, chemistry and evolution of the oil and gas industry. The price of fuel has risen sharply in recent months, by as much as 50% in some parts of the world. It's being driven by the conflict in the Middle East and growing uncertainty over global energy supply chains. This has a knock-on effect on all of us, because oil and gas lie upstream not just of transport, but manufacturing of materials as diverse as fertilisers and therefore food production. And rising input costs are being passed straight on to the consumer. Many nations are trying to mitigate this by exploring alternatives to hydrocarbon energy sources, but there are of course limits to what we can do right now in the short term, and the UK is no exception. There are calls from some quarters to renew drilling in the North Sea to tap into local reserves, for instance. We'll explore that later on. But first, geologically speaking, how does oil and gas form in the first place? Well, here's Jonathan Redfern, who's a professor of petroleum geoscience at the University of Manchester.
We need rocks that are rich in organic matter. And that organic matter is basically ancient life that was living in the seas, like algae, plankton, bacteria. But it could also be plant material, trees, leaves, woody material. So anything that's got organic component in there, because that contains carbon and hydrogen, and they are the building blocks for oil and gas. We call those rocks source rocks because they're the source of the oil. So we're looking for conditions on the Earth going back millions of years when we can generate those carbon-rich rocks. We're looking for an environment where we have lots of algae and plankton, typically warm waters. Now, when they die, they will land on the seabed and then can start to be buried. So over millions of years, those rocks will slowly get buried deeper and deeper and deeper. And as you go deeper into the Earth, the temperature increases and the pressure increases. On average, if you go down 1 kilometre, the temperature increases by roughly about 30 degrees Celsius. So when we go down, say, 2, 3, 4 kilometres, then we're at temperatures of typically 60, 80 degrees Celsius. And we also increase the pressure because of the weight of the overlying rock on the top. At that pressure and temperature, that organic matter will start to break down. And as it breaks down, it releases hydrocarbons.
Presumably this is a bit like Goldilocks then, isn't it? It's got to be just right in the sense that we need the right sorts of organic matter at the right concentrations, falling in the right sorts of geology so that it gets buried to the right extent with the right pressure at the right temperature for the right amount of time. And when all those conditions are ideal, then it cooks up into what we call crude oil.
Exactly. Geologists who are looking for hydrocarbons spend their time trying to identify where on Earth we may have had these unique conditions that give us these very rich source rocks, and where they've been buried to the right depths to be able to generate oil and gas and reach the right temperatures. And then we also have to think about where it goes as well, because in most cases, we're not looking for the oil and gas in the source rocks. The oil and gas is leaving the source rock, because when it's released as bubbles of gas or oil, it's then buoyant. It then really wants to make its way up to the surface. It's moving slowly over millions of years up to the surface. And probably most of the world's oil leaks out. Over time, it's just leaked to the surface and evaporated or got eaten by bacteria or something. But some of it is trapped in the subsurface. It gets to a point where it can't get to the surface. So there are rocks that do not allow the fluid to flow. We call them seals, impermeable rocks. The obvious one is salt. Nothing can flow through salt. So if you have a big unit of salt, then underneath that, any oil is going to be trapped. And we're looking for that oil trapped in the subsurface. And not trapped in small amounts, of course. We need to find it in millions and millions of barrels is what we're looking for. So very large amounts.
One question that often comes into us here at The Naked Scientists, especially at the moment because of what's going on, people say, Well, what's it like underground? Is there a huge, great bubble down there of oil? So when we then pull it out, do we leave behind this enormous hole in the ground? Or is it that it's almost like coral or bone marrow down there, lots of little holes and voids, and then they're stuffed full of oil and gas bubbles with the rock around them? What does it look like?
Most oil and gas is found in sedimentary rocks. So the two main types of rocks would be sandstones and limestones. Sandstones comprise sand grains which are cemented together, but in between the grains, there are holes. A sandstone is porous, so it's a bit like a sponge. And typically, the rocks we're looking at have got anything from 10 to 20 to maybe 30% of the rock is pore space, and the oil is trapped inside those pores. But the pores are connected so that the oil can move through from one pore to the next to the next. So when we drill into a sandstone, we drill from the surface, and then the oil will flow from the rock into the borehole and up to the surface, and it'll flow under its own pressure.
Why is it, though, that we've got some places where there's enormous amounts of gas and a relative paucity of oil, and others that there's absolutely loads of oil? If these processes just produce equal amounts or they're the same, why do you end up with some places dominated by gas and some dominated by oil? I'm thinking Qatar, for example, produces huge amounts of liquid natural gas, which supplies half the world from what I can make out. Why is that a hotspot?
There's two ways to produce the differences. One is that we have different types of source rock. So typically, we think that source rocks that are generated mostly from algae and plankton are more likely to produce oil because they're very rich in carbon and hydrogen, quite a high amount of hydrogen in the rock. Whereas other types of rock, for instance, coals generally, they've got less hydrogen in the organic matter. So they tend to want to produce, when they get buried, to produce more gas than oil. But the other thing is that with all source rocks, when you bury them, if they get beyond a certain temperature, then all source rocks will start to generate gas because at high temperature, the long chain molecules that make up oil start to break down, and they break down into the smallest molecule, which is methane. So it could be one of two things. It could be the original source rock that's more prone to generate gas than oil because of the organic matter in it. Or the second thing, it could be that it's been buried deeper and hotter, in which case all basins in the world, when any source rock gets buried really deep, it starts to generate gas.
And is that the same reason that people say that different oils from different geographies often have different, I don't want to use the word flavours, but characteristics? We talk about them being sweet and light or heavy. Is that why? Is that a reflection on the geology and the processes that have occurred during the formation of that hydrocarbon deposit?
Yes, exactly. It's the two things. So it could be related to the type of source rock originally. So, for instance, some oils are heavy, some oils are light. Right? We call them the light oils. We call them sweet oils because they're very easy to refine. And other oils, we call them heavy or sour. And also another thing with oils as well, sometimes they're associated with sulfur as well. Not a huge amount, typically a few percentage of sulfur, but that sulfur would have to be removed. So that's not so good for the refining. And that also reflects the geology where the source rock was.
Really interesting overview. Thanks very much to Jonathan Redfern. He's at the University of Manchester. We now know how crude oil forms, but how can it be turned into the stuff that we use every day? It's not just for fuel. Everyday products like plastics, synthetic fabrics, and even fertilizers are made from it. By engineering large hydrocarbon molecules into simpler species, petrochemistry begins the process of making many of the things we need. So what actually is in this black gold that is now holding the world to ransom? Will Meredith is an associate professor in chemical and environmental engineering at the University of Nottingham.
Essentially, crude oil is an unbelievably complicated mixture of a huge range of predominantly hydrocarbons, and they will essentially go from compounds with essentially one carbon, which is methane, right up to 100 or so carbons. And they can be straight chains, they can be cyclic structures, they can have branches on. So you have millions of potential structures, but the main ones that people will be familiar with are the things that end up in things like petrol and diesel, are largely the straight-chained hydrocarbons.
And what's the difference or the distinction between, say, petrol and diesel?
Okay, so within the refinery, what you're essentially going to do is sort of distillation. You're going to fractionate the crude oil by boiling point. Broadly speaking, that separates into different size fractions by their chain length. So petrol, or in the American term, gasoline, would be essentially something like C5 to C10 in carbon length, whereas diesel is a bit heavier. That would be something like C14 to C20. And that impacts on its combustion performance, on its viscosity, and that's why we have different engines optimized for different fuels.
And do different crude oils preferentially produce different fuels? So have you got some crude oils that are really good for making petrol and others that are really good for diesel or jet fuel and so on? Or is it just one big mix and we can make anything we want from anything?
Within the high quality fuels, the gasoline, the kerosene, the diesel, you essentially want is light crude oils, essentially things that come from the North Sea and also things that come from the Arabian Gulf. And then you have areas like the Canadian oil sands and Venezuela, which was also much in the news recently. Their oils are much thicker, much heavier. They're much more difficult to produce, and they need very specialist oil refineries. Things like from the North Sea and, as I say, the Persian Gulf, they're a bit more easygoing, and that's kind of why they have a higher value, both in terms of their composition, in terms of the value of the fractions that you can get from them, but also in terms of how easy they are to handle and produce.
And given that we understand the chemistry of this pretty well, and it's largely two atom types, carbon and hydrogen, why don't we just make this stuff synthetically? Do we need to be going to enormous risk and cost to get it out of the ground?
Essentially, work coming as I do from a chemical engineering department, that's a huge area of research. We've been exploiting crude oil reserves for hundreds of years, and so we've become incredibly good at it. And the fuel itself, it's so inert, it doesn't react with anything. A lot of synthetic, do a lot of research into bio-oils and sort of bio-based replacements in general. And whilst that is achievable, in many cases, it's a bit of a compromise. A lot of bio-oils, for example, might be a bit more corrosive than the fossil-based alternatives. They might be a bit less stable. They might be a bit prone to forming solids. And so the answer is yes, absolutely, we can synthesize these things, but it's essentially easier and cheaper to go the fossil fuel route, which is why that's still so important to the world's economy.
So what, biofuels are really not giving good old-fashioned oil a run for its money yet?
I mean, it's very much a case of priorities, I guess. I mean, you absolutely can synthesize and generate fantastic fuels. And as I say, there's a huge amount of research going into it. You can blend bio-based alternatives into fuel sources. So there is a lot you can do, but I think on a fundamental level, our systems are so optimized for the processing, the refining, and the utilizing of fossil fuels that, from an economic perspective, that is quite the challenge.
When we talk about the oil industry, most people think about the one contact they will have with oil, which is filling up their car or truck. But actually, it's when you see price shocks like we're having at the moment, and then that having a ripple effect through many different industries, you realise how plugged into every industry the oil industry is. Fertiliser and making things, etc., right through to the plastic that packages your lunch. So I guess the oil industry is going to be a really hard act to follow then, isn't it?
Very much so. I mean, certainly with the fertilizer story is the one that people were surprised to find that Qatar was a huge generator, but that's largely because the hydrogen that goes into the ammonia, that's produced from natural gas, from methane, and you can produce green hydrogen, but that requires huge energy input. And so it's that kind of balance. You can kind of almost do it the easy way, which is the fossil route, or you can develop systems, develop processes that use non-fossil carbon. As I say, many of which are achievable. It's just a case of where they are on the sort of technological evolution and where they are economically. That's the challenge.
It's not just hydrogen, though, is it? Because the other light gas is helium, and we get that from oil wells as well.
Indeed, we do. That's a very minor, if you like, a minor contaminant to natural gas, but it's also hugely valuable and hugely useful resource. When there was the war in Ukraine a few years ago, there was a helium price spike, and a real availability crunch. And at the university, we use it a lot for our analytical equipment, but perhaps more seriously in hospitals and MRI scanners and the rest of it. They have a huge use for it there. So that's something that is very much going to be a worry if the current situation persists.
All that glitters isn't just gold. Crude oil actually does that as well. Will Meredith there.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
This is the Naked Scientist podcast with me, Chris Smith, and today, as energy costs continue to spiral, we are looking at the oil and gas industry. What might the alternatives be? But first, given the current price of fuel, the UK government is coming under renewed pressure to explore alternative sources. One of those frequently touted is to open new oil and gas fields in the North Sea. Why pay someone else for their oil and gas when we could burn our own without the massive overhead of shipping it halfway around the world? Some argue. It sounds like a compelling point. The UK reportedly saved around £2.5 billion last year by relying on its own offshore gas reserves rather than purchasing imports of liquefied natural gas or LNG. But critics say it will hammer the UK's attempts to reach its climate change targets. But how much oil and gas is actually out there? And do the sums really add up? Well, John Underhill is the University Director for Energy Transition at the University of Aberdeen.
So in the early days, and we're talking here about the late 50s, there had been exploration onshore and hydrocarbon oil and gas discoveries made both in the UK and in Holland. And people looked out into the North Sea and wondered whether the two areas could be connected. But it wasn't until the mid-60s, after something called the Continental Shelf Act, that actually you could go out into the North Sea to undertake seismic surveys from boats, to get 3D body scans of the subsurface, identify places to drill, and then test that. And the first well was drilled in the southern North Sea in 1964. And after the discovery of gas in the southern North Sea, people moved into deeper water in the very late 60s and early 70s, into northern, harsher, deeper waters, exploring for oil.
And who has access/right to exploit that?
So it was companies like Shell, BP, ConocoPhillips, Chevron, Total. That has changed in recent years as the North Sea has reached maturity and production has declined and exploration opportunities are few and far between, and indeed at the moment not encouraged by the UK government.
What is it about the geology in that tract of coastline that means that those deposits are there at all?
For the southern North Sea, we have coal measures which are gas prone that have been buried sufficiently deeply that charge their gas, it rises, it's buoyant, into reservoir sandstones, largely of Permian age, capped by salt deposits, which is a very effective seal to keep the gas in. So that's what works in the southern North Sea. In the northern North Sea and central North Sea, we have an oil-prone source rock. It's called the Kimmeridge clay, and it's Upper Jurassic in age. The subsequent burial of which has led to it being heated up to 90 degrees centigrade or more. Then hydrocarbons have expelled from that out of the basin towards the basin edges, and in so doing have gone up effectively a staircase to fill and spill and fill and spill the traps that again contain a reservoir seal pair, and in so doing it's become a highly effective petroleum province. At one stage, the North Sea was the fourth largest in terms of production of all the basins in the world. That's how effective the system became.
You were saying it was a major leader in terms of production, but how much was coming out of there? And how much did we start with? And how much critically is left?
From the North Sea in totality, what's called 95 billion barrels of oil equivalent, roughly split half and half between the UK and Norway. All the main fields, the large fields, were found early. And so all the big fields, places like the Brent Field, Forties Field, and so on, most of those were found in the very early years of exploration. And I'm talking here about the 1970s. They came on to production in the late 70s through the 80s and the 90s. And so the UK became self-sufficient in oil and gas up until the early part of this century. But since then, both our oil production and our gas production have been in an inexorable decline. And we're getting towards the tail end of the basin. So it is mature. We're coming towards the end game. It doesn't mean to say that there isn't oil and gas still to be found that could be extracted, but it is no longer the prolific basin that it was back in the 1980s and 1990s.
Will the current economics provoke a rethink or a re-evaluation of that?
We wouldn't want to be in this position, but the inconvenient truth at the moment is that we rely so much on oil and gas for our total energy and for our electricity that we have to get it from somewhere. Either we import it, and potentially, if we don't bring it from Norway, which has a lower carbon footprint, we bring it from other countries which have that higher carbon intensity and worse for the global climate.
So why do we do that? What's the motivation? Why are politicians so married to sending pounds overseas to buy other people's gas and burn that with its carbon footprint? Why don't we use our own?
Many in this country would wish to see us wean ourselves off oil and gas. Quite understandably, we want to go to a lower carbon system, but we need to be realistic, pragmatic, and solution oriented, because it is unfortunate that we rely so much on oil and gas. And currently, the North Sea is considered by companies to be uninvestable because a windfall tax was brought in 2022 at a time when they were admittedly making big profits. You can understand why that was the case. But when windfall conditions passed, the windfall tax was not removed. And as a result, companies have been leaving the basin, and it does lead us to bring more imports with the higher carbon footprint and the detrimental impact on global climate. Unless the fiscal conditions change, unless the basin becomes investable again, and we go to a new regulatory and taxation regime, then we will see a continued demise of the North Sea oil and gas sector, at least in the short term, until we get to the point where we have a robust, reliable and secure new energy system, if you like, but based on a renewable future to provide the electricity in particular that we need. Then unfortunately we're not going to see oil and gas, domestic oil and gas being developed.
How many years, if we were to improve the fiscal outlook for companies, how many years of reserves have we got out there that we could plug into?
We can arrest the decline if we change the fiscal regime. And if that were the case, then you would see oil and gas continue to be developed in the North Sea to 2050 and beyond. And the North Sea could provide more of that rather than the imports that we would get from elsewhere.
Fuel for thought. That was John Underhill at the University of Aberdeen. Now, to end where we came in, the conflict in the Middle East has put our reliance on oil and fossil fuels in general into sharp focus. They are not long-term options for energy provision, and climate change and pollution also mean we need to be actively exploring other avenues. But what might those be, and how do we transition as painlessly as possible to an oil-free future? We asked Richard Black, a former BBC correspondent and Director of Policy and Strategy at Ember, to take a look at our other options and how they might compare.
If you look in terms of the amount of energy that these fuels contain, what is called primary energy, then they're supplying something like 80% of the energy that the world uses. So that's a big hole to be filled. Fortunately, it's not actually quite as bad as that, because fossil fuel burning devices, whether it's power stations, cars, whatever, are quite inefficient. Well over half of the energy in those fossil fuels is wasted. And actually, the alternatives that we have now, such as wind turbines, electric cars, batteries, etc., are far more efficient. So it's not an 80% hole that you need to fill, it's maybe 30, 40%, that kind of thing.
How does it break down in terms of uses? So you say there's about 80% energy, but energy goes into transport, it goes into heating, it goes into industry. What does that look like?
Yeah, I mean, it varies by country, and there are different ways of sort of cutting the cake. But as a ballpark, we've got transport, which is a big user. We've got industry, which is a big user. We've got cooling and heating, which is a big user. And then we've got the energy industry itself, because the energy industry actually needs energy to get the stuff out of the ground, transport it around the world, and so on. So when you're thinking of how to replace the fossil fuels in total, then you've got to think about all these different applications. Fortunately, there is a vector, as scientists call it, a thing, that can do virtually all of that. And it's a thing that we're very familiar with, and that is electricity. So if you take the humble car, the majority of the cars on the roads of Britain and every other European country, bar one, are mainly powered by petrol and diesel. But increasingly, electric cars are absolutely realistic. It's a real thing. And it's coming to, if it's not already coming in a street near you, it's coming to you very soon.
So you're substituting, when we talk about the energy equation and we regard oil and gas and coal as an energy supply, you're saying, well, we can substitute some of that as electricity. And therefore you can say, well, where do we get the electricity from? And that can be some renewable and alternative sources. The problem is that many of those, solar is an example, wind is a good example, which the UK has invested in very heavily, they're not always available. So many people will say, well, we need a gas backup because when the sun doesn't shine, like at night, when the wind doesn't blow, like some of the time, we need to be able to turn that energy supply on from alternative sources.
Yes, I mean, there is a future where all of the electricity that is used in pretty much every country in the world does come from wind and solar mainly, with ingredients from hydropower, geothermal, maybe a bit of nuclear here and there, and then what are called flexibility mechanisms. So the main problem, as you're alluding to there, Chris, is that with wind and solar is that you can't turn them on and off at will. So you need to be able to bridge those gaps in some way, but gas backup is only one of the ways of doing that. And there are four, as they're called, flexibility mechanisms. So one is simply that you switch off non-essential uses at times when generation is low. This is something that's called demand response, and it's used quite a lot in various countries, including the United States. And basically, it's a bit like, if I buy a ticket for the train, I can buy a ticket in rush hour at 7 in the morning and it's going to cost me a lot of money. Or I can decide not to do that. I'll go at 10 o'clock instead because I don't need to be there bang on time. And it's going to cost me a quarter of the price or something. Well, if you feed this price signal through into electricity bills, you get the same thing. Do I need to run my dishwasher at 8 p.m. in peak time of peak load? No, I actually don't. If it's cheaper, I'll run it sometime in the early morning. That's fine. So that's demand response. The second one, which is really coming up fast, is storage. The main historical way of storing energy for electricity systems was something called pumped hydro. There are quite a few stations around Britain. And basically, when you've got abundant electricity, you pump water uphill from a low reservoir to a high reservoir. When you need electricity, you reverse. The water comes downhill and generates electricity. So that's there. But the big new player is battery storage. Increasingly cheap. Prices have come down by something like 85% in a decade. The amount of volume being deployed around the world is going up. It's not quite doubling every year, but it's that kind of ballpark. The third way you do things is by sharing electricity. So you connect electricity systems with big long cables. In the case of the UK, they have to go under the sea. The UK's got, I don't know at the moment, 7 or 8, I think, cables linking it to other countries. So you're basically sharing electricity and you're getting around some of the shortages that way. And then the fourth system is you have to have some kind of long-term storage. And a lot of those systems are basically in development. But you can also do things like making hydrogen. And then in extremis, you burn the hydrogen in a hydrogen burning power station. So you don't have to have gas backup. It's just one of the means that's available.
But in our country, the weather's appalling half the time. And so you just don't have the solar capacity. So we do need some kind of surefire way of getting that energy. If solar is going to pay dividends, perhaps placing solar panels in big arrays on the Sahara, which is a project that's undertaken at the moment, isn't it? And shipping that electricity long distances, that's coming. But what sort of timeline are we looking at? Because energy prices are incredibly high at the moment. They're being made even higher by what's going on geopolitically. And as a result of this, people are saying, look, I know we've made great progress with recyclables, but there are limits, and we really need to be tapping into an energy source that will drive prices down in the short term while we iron out these bumps. So what sort of timeline are we looking at with these sorts of things?
Well, I mean, for those projects in the Sahara, it's really a question of when investors gain enough confidence to plough ahead and build it. I mean, there was a project, I remember 15 years ago, that was posited to build solar panels in North Africa and bring electricity into modern Europe. And it didn't happen because in the end, for whatever reason, the investors didn't think it's worthwhile. I mean, we're talking big sums of money here, multiple billions. So it's very hard to give a timeline on a project like that. One thing that's very important to realise at the moment is the high electricity prices in the UK are primarily a result of the way that the market is designed. So for any given period of time, half hour or whatever, the price of electricity is set by the most expensive generator that is supplying electricity at that point. So you can have a situation where 90% of your electricity is coming from wind turbines and nuclear reactors, 10% is coming from gas, but everybody's having to pay the gas price for all of their electricity. So this is something that, energy professors have been talking about in the UK and other countries with a similar market structure for years. And the government has recently begun to talk about changing that. So basically people benefit from the cheaper renewables.
Richard Black from Ember there. Let's all hope things settle down soon. We'll be back on Friday with the latest science news stories from the week, including how a 63-year-old Norwegian man who's known as the Oslo patient has become the latest patient to be cured of HIV with a bone marrow transplant. But this case is strengthening our views that how we thought the process was working in the handful of patients treated so far might not actually be the case. Find out why on Friday. And next week, while we're talking about what's coming up, we'll be launching the Mosquito Minute, where we'll bring you the very latest in mosquito and malaria research from around the world. Meanwhile, if you like what we do please head over to nakedscientist.com/donate. Your contributions really do matter, and we really appreciate the kind support. I'm Chris Smith. Thank you for listening, and until next time, from all of us here on the team, goodbye.